Next problem was to prove that if G is abelian and A and B are in G, arbitrary elements, then A times B to the n power is A to the n times B to the n, and we'll restrict ourselves to all natural numbers, positive integers, just to make it simpler. It's still true for 0. It's actually trivial when n is 0, because by definition, just like any non-zero number to the 0 power is defined to be 1, so any group element to the 0 power is defined to be the identity. It's also true when n is a negative integer, but just to keep things simple, let's just prove this for positive integers. It's an induction proof, base case. If we're talking about the natural numbers, would be n equals 1. When n is 1, it's trivially true because ab to the first power by definition is a times b, which can be written as a to the first times b to the first. There's nothing really to do. Inductive step includes the inductive hypothesis. I could call this inductive hypothesis. Assume ab to the k equals a to the k, b to the k for some integer k, some positive integer, some natural number. Emphasis on the word some. We must show that this kind of equation is true when k gets replaced by k plus 1. Then ab to the k plus 1. Well, first of all, by definition, that's ab to the k times ab. By the inductive hypothesis, that's a to the k, b to the k times ab. Inductive hypothesis. I called this whole thing the inductive step, but again, you could call it the inductive hypothesis as well. This first line, the assumption is the inductive hypothesis. We've never used the fact that G is abelian so far. Well, use it now. Rearrange this. If you want to show an extra step, you could do that. G is abelian. And by definition, that's a to the k plus 1 times b to the k plus 1. Therefore, by the principle of mathematical induction, PAMI, I've never done that before. For short, principle of mathematical induction, ab to the n equals a to the n, b to the n, for all n in the natural numbers, for all positive integers. Emphasis on the for all. Praise the Lord. What would you do in the case when the exponent is negative? When the exponent is negative, let's pick up just a particular example of a negative exponent, like a to the negative 4 or something. One thing you have to do when you think about negative exponents with groups is you have to realize that by definition, this can be thought of in one of two ways, either as the inverse of a to the 4th power, or a to the 4th inverse. That's one thing you have to do if you try to prove this for negative exponents. The other thing that you can do is you can actually use induction again by effectively working induction backwards. The base case would be when the n is negative 1, assume it's true for some negative integer k, and show it's true for k minus 1 instead of k plus 1. There are some ways to relate it to induction for positive integers as well, but that's one thing you could do. A little tricky, but it can be done. You might wonder, if G is not abelian, what does AB to the n power equal? if G is not abelian. If G is not abelian, or you can say non-abelian, what does a b to the n power equal? It doesn't necessarily equal a to the n times b to the n. That could be true for some of the elements, but not all of them. Well, you can't really say much here beyond just saying essentially it equals ab times itself n times if n is a positive integer. Technically, you can get rid of all those parentheses and write AB, 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 blah, 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 AB, where there's n A's and n B's. But that's not very insightful. Like, how do you simplify that? In some circumstances, it can be simplified. But in the abstract, that's really all you can say.